So with all the things that we have learned, starting from electrical field line, the density, the area vector, the flux and everything, we have a theorem. Finally, we have a theorem. This is starting point of your all the derivations. So this theorem is your Gauss's theorem. So the basic funda is this. If I have a closed surface, like say this, it can be any structure. If I happen to see, say, 2 field line going in and say 3 field line coming out, I can definitely tell that the net charge inside this is positive. But if I see same number of field going in and same number of field going out, the net charge will be 0. Does it make sense? And if I see more field lines going in, but less field lines coming out, I can tell that the net charge is inside the surface. It's negative. Inside is negative. Does it make sense? Because negative charge has field lines going in, positive charge has field lines going out. If there is imbalance, then there is a net charge. If there is no imbalance, then the net charge is 0. That's what Gauss's theorem talks about. Again, why is it so and all? It should be commonsensical now. Of course, the scientific reason and everything. There are plenty of explanations. But main thing is it's common sense, right? So Gauss's law says that the total amount of electrical field coming out of a closed surface, this is a closed surface, there's no opening, it's directly proportional or directly dependent on the total charge enclosed by that surface. If there are more positive charge, number of field lines, if there are more positive charge, more field lines will come out. And if there is 0 or 0 coulomb, equal lines go in and come out. Again, I'm putting it a very simple manner, but it is all of this is right. So you can draw this example for negative, for positive you can write the statement, for 0 you can write that statement. Now let's see the official statement. The net electrical flux through any closed surface is proportional to total electrical field charge enclosed within that surface. So let me put it in mathematical way. The net electrical flux is equal to, right, the closed surface and the field lines that is coming out. And this entire thing is proportional to the charge that it encloses. As simple as that. So when we remove this proportionality symbol, we end up with the constant, and that is our old friend epsilon naught. So basically, your phi E flux is equal to Q by epsilon naught. Again, it's a very simple manner. It's the simplest of all of them. So we're going to see a lot of complex ones. But the idea remains the same, and we'll see how to make use of this. Okay, guys. So before I move on, everywhere we have this, surface. So this Gauss person's name is also related to those surfaces, and that is your Gaussian surface. So it's an imaginary closed surface enclosing charges or no charges. The surface is called as Gaussian surface for that charge. So we have, say, a bunch of charges and it is enclosed by some space, some surface, three-dimensional surface. So for this set of charges, this surface becomes the Gaussian surface. So for these charges, right, this is the Gaussian surface. Reason? Because it's inside that. Because it's inside that. Now, one idea is that it's always clever, or it's always intelligent for us to use Gaussian surface, which kind of gives us some kind of symmetry and helps us solve things. Again, the basic idea of superposition theorem and everything, adding up everything, right? So all of that will come together in the next set of topics. So whenever we talk about, say, I want to give an example, say a line charge, we make use of cylinder as our Gaussian surface. So this is our charge, and that's our Gaussian surface. Like this, we have quite a few structures and quite a few Gaussian surface to help us integrate and everything. Simplify this basically. Simplify this. Okay. Yeah. So let's have a look one last time. We are looking at trying to figure out the electrical field through complex structure. And to do so, we make use of electrical field line. When it comes to field line, we look at density, we have to look at directions and everything. To help us with that, we learned about area vector, flux and everything. Along with that, we need to make use of one common aspect in nature, and that is given by your Gaussian theorem. He observed it, and now we have the theorem on that. What this person told us, if you're looking at charge enclosed within a space, if we see more number of field lines going in than coming out, it's negative charge inside that space. Positive charge if more field lines comes out, and zero charge, that is the net charge is zero, or there is no charge inside the space if there are equal number of lines going in than coming out. So mathematically, it's as simple as this. The flux, the net flux through any closed surface, it's directly proportional to your charge that the surface encloses. Does it make sense? Flux is given by this set of expression, and we can see here closed surface and all of that. So we can equate this. And when we remove the proportionality constant, it's epsilon naught. And there's a very simple version of what we are trying to do. So this will not get too complex though. But yeah, it can get complex for different structure, but we are not studying all of them. To help us with all of this, we have to make use of surface, obviously. And this surface is given a special name, right? Gaussian surface. For these set of charges, right? This particular structure, whatever this is, I mean, this is supposed to be prism, but that's your Gaussian surface. It can be anything. A small note telling that whenever we considering Gaussian surface, we should consider it in a way which helps us in integration. So for example, for a line charge, we can use a cylinder structure to help us integrate. Again, when we take up few derivations, it will make a lot of sense. For now, just copy this.